All right, so double and triple bonds, just quick review of single bonds. We'll work through the diagramming on this, and then we'll look at some examples together. So the simplest way for atoms to covalently bond is a single bond. We saw that on the previous activity. It involves sharing of a single pair of electrons. It is also possible for atoms to share 2 or 3 pairs of electrons within a molecule. And we're going to look at a couple of diatomic molecules to see why and how this double bonding or triple bonding can result in a stable molecule. So I were to start with oxygen. Oxygen is diatomic. It's going to make an O2 molecule. And we want to think about how that's going to work out and how the octet rule is going to work out. So I'm going to zoom a little bit, and we're going to work with this diagram here. So if we check oxygen's position on the periodic table, oxygen is in column 6A. It has 6 valence electrons. And so I might just start by doing the dot diagram like we always have. So one, whoops, it's going to work. It's not drawing. Oh, there, caught up. That was weird. Okay, try that again. All right, so it's going to have 6 valence electrons, which I might fill in like this: 1, 2, 3, 4, 5, 6. The other oxygen is going to have 6. I'm going to kind of draw it in such a way that it has 2 lone electrons pointing at each other. So it needs to have 2. I'm going to do kind of mirror image. Pair, pair, single electron, single electron. And our examples of single bonding, we just kind of imagine those 2 atoms overlapping their electron clouds, which would result in something like this. So you don't have to color code yours necessarily, but we've got the 6 electrons from the left-hand oxygen, and then we've got the 6 electrons from the other oxygen. And we're going to think about this as a shared pair. So we share electrons with nonmetals to get to an octet. An octet will be a stable situation. So if I kind of check where I am with this, right? If I were to circle that side, it has access to 2, 4, 6, 7 valence electrons. The other side has access to 2, 4, 6, 7 electrons. So the octet rule is not satisfied. So a single bond is not going to work in this case. So what do? What we need to do is share additional electrons. So if I imagine, this electron kind of moving up into the bonding region, and this is something that you can do in the Play Meta game, we think about what that's going to result in. Now we've got non-bonding pair, non-bonding pair, and I've shifted the other one up as a bonding pair. It still has 6, but I'm thinking about sharing 2 of them instead of just 1. On the other side, I've done the same thing. So I've got non-bonding pair, non-bonding pair, and I have 2 electrons here that are going to be able to bond. So if I kind of check myself now, if I circle all the non-bonding and bonding electrons on either side, that side has 2, 4, 6, 8, an octet. This side has an octet, 2, 4, 6, 8. And so the octet rule is followed. That's going to be a stable structure for the molecule. All right. Now, how do we draw that? Zoom out again a little bit. Remember that a single bond was shown with a single line. this has a double bond. So I want to write the Lewis structure as an oxygen and an oxygen. Now with a double bond, because we're sharing 2 pairs of electrons. And then I still want to show the non-bonding electrons. Now, we'll get into this more, but the way we typically draw non-bonding electrons is we think of them as having negativity, right? They're negative electrons. Negative electrons repel from one another. So I have these kind of negative region, between the atoms. And then I've got these non-bonding electrons that will push away from each other as far as they can go. So typically you will see those drawn something like this, kind of pushed out in the diagram as far away from each other and the bond as they can get. It's not wrong to draw it more like this, but this is a good way to think of it going forward. So that is our oxygen molecule O2, double bond required to get the octet rule followed. Okay. All right, moving on. Oops. Nitrogen. So nitrogen is also diatomic. In other words, it's going to be a molecule N2. 2 nitrogen atoms bonded together with shared electrons. This is going to be an example of triple bonding. So we're going to kind of work through this in the same way we just did and see why we need a triple bond for nitrogen. So nitrogen is in group 5A, 5 valence electrons, which we would normally draw as 1, 2, 3, 4, 5. Same thing on the left, 1, 2, 3, 4, 5. If we just simply overlap them like we did with single bonding, we've essentially got that on the left, no change. Shared pair on the right. Again, if we check our octets here, we've got 2, 4, 5, 6 electrons available to the left atom, and same on the right, 2, 4, 5, 6. That is not going to satisfy the octet rule. Okay, so we're going to do the same thing. Let's think about shifting these in as bonding rather than non-bonding electrons into the middle. We'll see what that looks like. Kind of redoing this. So we've got 1, 2, 3. And now I'm going to have 2 bonding electrons. So it's still 5. Okay, I didn't add any electrons here. I just kind of shifted where we think of them as in the diagram. The one on the left still has the 2 non-bonding on top, a non-bonding on the left, but it is now added in another bonding electron. So we should see this is better, but it's still not an octet, right? So if I'm taking inventory here, all of those electrons are shared. So this nitrogen kind of has access to those, but it's 2, 4, 6, 7 available to it. And then the one on the left, 2, 4, 6, 7. So again, 7 is not an octet. The octet rule is not satisfied. So we're going to have to take this other non-bonding electron here and actually move it into the bonding region. So it's going to be something like that. And this should give us our octet. So the nitrogen on the right had its non-bonding pair up here. Now it's actually shifted in 3 electrons to the bond. Same thing here, non-bonding, 3 electrons involved in the bond. So now if we check our octets, 2, 4, 6, 8, and 2, 4, 6, 8. Octet rule is satisfied. So the Lewis structure is going to have 2 nitrogen atoms, triple bonded, 1, 2, 3 lines. That represents 6 total electrons, 3 pairs. And although we had the kind of the non-bonding electrons on top, you will almost always see it written like this with the non-bonding on either side. And the idea is these are negative electrons. They're going to get as far away from each other as possible. The bonding region is negative, and so it's going to kind of push those electrons out to either side. So that is our N2 molecule. The octet rule is followed. All right, any questions at that point? All right, so let's look at some examples. Kind of a new set of guidelines for how to solve these Lewis structures when we are going to have the possibility of single, double, and triple bonds. Okay, we'll do 2 examples together, and I think it'll help. So the first thing you need to do is find how many total valence electrons you have. And that's by just looking at the formula, looking at the periodic table, adding them up. It's a good idea to start with a single bond between the central atom and the other atoms. Sometimes you'll luck out and single bonds will work, kind of like on the previous activity. Sometimes they don't. If you kind of run out of electrons on step 3, so step 3, once you've formed your single bonds, is try to fit in the remaining electrons to satisfy the duet rule for hydrogen and the octet rule for the other atoms. You may run out. You may not have enough electrons to make it work with single bonds. If that is the case, so if the duet rule and the octet rule can't be satisfied with single bonds, you have to start trying combinations of double and triple bonds. Okay? It's kind of like a puzzle. You might get it on the first try, you might not. You might struggle with it a little bit. The more you do these, the easier they get. Okay? Another important tip, try to keep symmetry when you can. So you don't want to have a bunch of electrons on like the one side of a molecule and not a lot on the other. And then your electrons will always be in pairs. So we're not going to have individual electrons by themselves. Okay. All right, so carbon dioxide, very common molecule. 1 carbon, 2 oxygen. Okay. So the first step is to tally up the valence electrons. So carbon, if we find it on the periodic table, should have 4 valence electrons. I'll put 4 VE. Oxygen is in column 6A. It has 6, but there are 2 of them. So they are going to contribute a total of 12 I said that with a twang, 12 valence electrons. Okay. Altogether, in the structure, I need to have 16 valence electrons. 16 electrons are available to try to satisfy the octet rule. So the tip was to start with your central atom. The central atom here is going to be carbon because there's only 1 carbon in the compound. It should bond out to 2 oxygen, which are going to be kind of bonded outward from the center. Okay. The next tip was try to form single bonds first. Okay. So there's a couple ways to do this. You can just count them out and draw it. I'm kind of like a kinesthetic or visual learner. I like to actually think of these as things that I can manipulate and move around. So what I've done here is created a dot that allows me to just keep dragging additional dots out. Okay, and each dot is going to be an electron. And some students who like this technique, I actually have these little plastic bingo chips that you can use to work these out. If you're more of kind of a hands-on person, this might be helpful. But what I need to do is I need to bring 16 of these electrons into the structure, and I want to start with single bonds. So I'm going to bring in 1, 2. That would be a single bond between that oxygen and carbon. 3, 4 of my 16. That would be a single bond. And then I start to try to bring the electrons in, the rest of the 16. I try to do it in a symmetrical way to see if I can get the octet rule satisfied. So I'm going to bring in and keep them in pairs. So I've done 4. That's electron number 5, electron number 6, To keep it balanced, I'm going to go electron number 7, electron number 8. None of these has an octet at this point, but I've used 8 of the 16. I'm going to go 9 and 10. Keeping it symmetric, I'm going to go 11 and 12. $13, $14. And now that oxygen has an octet, right? But I've only used 14 of the 16. So keeping it symmetric, I'm going to go 15 and 16. That is the total number of electrons I can use. Let me check for my octet. This oxygen would be good, right? It has 8 electrons available to it. This electron or oxygen would have 8 electrons available to it. But we have an issue with carbon. Carbon only has access to 4 electrons. So how do I solve that? I can't just add electrons. I've already used all 16. I need to start to try to form some double or triple bonds. So if I take one of these non-bonding pairs and I shift it into the bonding region, that would be good for carbon. Keeping it symmetric, shifting that in. What I'm essentially doing is taking these and moving them in as bonding electrons. All right. So what that's going to do is make carbon in the center with a double bond on either side. That would be a total of 2, 4, 6, 8 electrons available. And then I need to keep track of what's left. I've got my oxygen over here, my oxygen over here, 2 non-bonding, and another 2 non-bonding, 2 non-bonding, and another 2 non-bonding. That is my Lewis structure. Double bonds are required to get an octet for each oxygen and each carbon. So it's kind of a trial and error thing. I've done a lot of these, so I kind of knew where to go. You might struggle at first, to be expected. We're going to practice these quite a bit. Okay. All right. We didn't get to the second example. I may post a video of that later today. I'm going to go ahead and stop recording